So a few, there we go, disclaimers at the start. First of all, the views that I will express are really my own, and so they shouldn't be taken as, official word from the Department of Energy, of course. And I would say the speaker continues to be an avid student of all the marvelous nuclear science research ongoing in the United States. That's a polite way of saying I don't feel that I'm an expert on any of it, but I do try to learn as much as I can about all of it. And so if you find that something is not quite right, you're more than welcome to correct me. Another point, when I look at the future of nuclear physics in the United States, some things are reasonably clear, but I find that there are also questions that are not answered at the moment, and I don't think I'm the only person who has these questions. When I talk with some of my good theorist friends or others in the field, they have questions as well, and at least I'll pose one of those as we go along. Some of my comments are intended to be a bit provocative and to get your feedback. And the talk is largely organized around the 4 discovery science portfolios within our office: heavy ion, medium energy, low energy, and nuclear theory. And so, as some of you may know, since 2010, our office has also been the steward of isotope production in the United States. And when that came over to our program, we restarted isotope research. Prior to that, there'd really only been production for sort of rare isotopes for national needs. But the person who took on that responsibility, Joanne Gillow, restarted isotope research. And so, but I will comment on that briefly, but basically deal mainly with the discovery science portfolios. And I'm going to attempt to focus on science, not budgets or politics, because those things are really beyond the scope of what any of us can control. Or, we could debate a long time about what if this, what if that. We'll show a little bit of budget, but I'm going to try to first order to stick to science. I'm having trouble advancing. There we go. So first slide I wanted to show is this one. For one reason, it took me a long time to make it, so I want to use it. And so, and what I'm showing here is the breadth of the discovery horizon in present-day nuclear physics in the United States, which I believe is quite broad. I've said this is not your father's nuclear science. I actually looked up the other day the origin of that saying. It was from 1988, and it was about Oldsmobiles, and it turned out to be actually a very poor advertising slogan because it became so familiar that everybody used it for something different, and Oldsmobile didn't get their money's worth. But anyway, in nuclear physics today, it's a quite broad, vibrant program that touches on the evolution of the universe all the way from sort of the electroweak era, when the fundamental symmetries were sort of shaking out of the earliest moments of the universe. And so we have parity violation experiments, for example, at Jefferson Lab, which touch on whether or not there's physics beyond the standard model coming from that era. We have, of course, the RIC program, which we all know sort of addresses the state of matter that existed a few microseconds after the universe was born. And we go all the way to the present day when, research at Jefferson Lab is showing that nuclei have neutron skins, and that may affect our understanding of how neutron stars exist today. So we have a very broad, very exciting portfolio in nuclear physics. And I guess one comment I would make is I see us largely being able to continue that breadth into the future, and I think it's important that we try to do that. Fortunately, I don't have to come up with all the thoughts on where nuclear physics is going in the future. Every 5 to 10 years, well, 5 to 7 years, I would say, not 5 to 10, we get together some of the best and brightest in the field and ask them their opinion on what's important, what should we be trying to do. And so this is from the 2007 long-range plan, which was called the Frontiers of Nuclear Science. And the first 3 bullets are the 3 frontiers that were identified in that plan. And then there were a number of very important questions that the plan outlined that nuclear physics had to address in the coming 5 to 10 years. And so there's actually another group of questions in nuclear structure and nuclear astrophysics that we'll come to later. But what I would like to do is to sort of use this as a bit of a template as I go through the different subprograms and try to identify which parts of this outlook that a given subprogram is going to address going forward in the future. And the one I'm going to start with is medium energy. And so what you see in red text and underlined in red is, at least from my view, what I think that subprogram is on the hook for answering. And so, for example, in the case of medium energy, they should certainly tell us about the internal landscape of the nucleons, what governs the transition of quarks and gluons into pions and nucleons, and the role of gluons and gluon self-interactions in nucleons and nuclei. They may have things to say as well about fundamental symmetries and why there's now more visible matter than antimatter in the universe. What were the unseen forces present at the dawn of the universe? So I've put question marks there. I think they may have something to say about that, but the fundamental things they're really sort of baselined to answer, to use a DOE parlance, is on the left side, and it's underlined. So when the science director or the associate director for science, I'm not sure if that's exactly the right title, but Bob McEwen sort of talks about Jefferson Lab, the picture he presents is this one, that with some justification, I think, that the laboratory is not just focused on the quark structure of nucleons and nuclei, but it has science components that touch the other subprograms in nuclear physics. And so in nuclear structure, for example, I gave an example a moment ago. One of their important experiments in PREX is sort of focused on whether or not nuclei have neutron skins. One of their focuses coming up will be, of course, from the Hall D program, QCD and how things hadronize. That's certainly of relevance for the quark gluon plasma, where we basically recreate the early moments of the universe, but then everything has to hadronize in order to show up in the laboratory. They have experiments that address fundamental forces and symmetries. I'll talk about two of those in a moment that are an outlook for the future. And they have a very strong theory program, both in sort of analytic theory, but also in lattice QCD. And so you see an example shown there concerning quark confinement and lattice QCD analysis of how that happens. They're also very innovative. They've used graphical processing units. I think they pioneered the use of graphical processing units to do lattice QCD calculations. They, of course, have a strong competency in superconducting RF acceleration cavities and important spin-offs such as in the area of medical imaging. So it's sometimes, at least I in the past have tended to think of it as fairly narrow in terms of just the quark structure of nucleons, but I think actually the correct picture is more this one, that it actually has broader impacts and touches other areas of nuclear physics. One of the important new capabilities that will come with the upgrade of the facility to 12 GeV, which is ongoing now and should be completed in the FY15, FY16 timeframe, is a new hall, Hall D, and the detector in that will be focused on it's a tagged photon beam that will be looking for exotic mesons that can result, for example, from gluon excitations and exotic JPC numbers that one couldn't get in just the QQ bar pairings. So that's an important upgrade that's ongoing. Parallel to that, there's, as I said, a very strong lattice QCD effort, and so this is an example of ongoing efforts to calculate the isovector meson spectrum. And you see that they're improving and extending previous measurements. So this is, I would say, work in progress. This is still giving a pion mass that's well above the physical pion mass. But I think what's really powerful here, if you ask my opinion going forward in the future, is the promise of significant advances in lattice QCD, meaning sophisticated, more precise, larger calculations, combined with the experimental data from Hall D. And I think this is going to provide a new window on some fundamental processes that we would really like to know about. So initially from the lattice QCD, we expect to get the spectrum of states, for example, for gluons and glue balls and exotic mesons, conventional mesons and baryons. And as I said a moment ago, significant strides have already been made, although the up and down masses and hence the mass of the pion is still too high. But for example, as this becomes a more powerful and more a tool with higher fidelity, let's say, to the physical world, we could, for example, the flux tube and constituent gluon models make different predictions for the spectra of hydrids. And so we can actually test, using their lattice efforts, which of these is closer to the correct view. So I think we will get a deeper understanding of physical process. One of the things that they need to do to realize this goal will be predicting the photocouplings of these states and predicting their strong decays. So this is sort of new territory at Jefferson Lab. And what final states these exotic mesons can be seen in and how broad they are. The production and these production and strong decay questions are crucial and largely untouched to this point for the glue balls and hydrids. So this is new activity that's ongoing. So when you ask me future of nuclear physics, I think one of the important things that we'll see going forward is productivity in this area. It's particularly strong because of the combination of the experimental and theoretical work together. There are, however, so I'm leaving out a whole suite of ongoing smaller experiments, and so I won't touch on those, but certainly if you're interested, you can find them on the Jefferson Lab site. I'm sort of picking a few things to highlight. One of the possible experiments for the future is called Mahler, and so this would be an experiment to measure parity-violating electron Mahler scattering, and looking at the fractional difference depending on the polarization of electrons scattering off atomic electrons in a liquid hydrogen target. That asymmetry is proportional to the weak charge of the electron, which is in turn proportional or is a function of the electroweak mixing angle, sine squared theta W. And so this potentially has a world-leading precision that it can achieve, on par with the best measurements of the same parameter at electron-positron colliders, and could put a new window on physics beyond the standard model, loop diagrams for particles that we conjecture but haven't observed yet. Similarly, another longer term, so these are in, I should say, these are in the sort of $20 to $30 million class. Okay, that's sort of why I'm picking these, because they're relatively big pieces. Another longer term possibility is something called the solenoidal large intensity device, or SOLID, which looks a bit like a fixed target version of STAR, as far as if you don't look too closely. So it actually can be configured differently. You could put the target sort of in the middle of it, or you could put it onto one side. And there are different programs people intend for it if it moves forward. One is parity-violating deep inelastic scattering. Again, you have sensitivity to sine squared theta W. You have sensitivity to searches for Z primes or compositiveness or leptoquarks. So very much trying to address the question of, what's the physics beyond the standard model that we all suspect is out there. It also has a semi-inclusive deep inelastic scattering physics menu, and you can read it there. Unprecedented precision in three-dimensional mapping of single-spin asymmetries. Combining with class 12 GeV photon and world data, it can extract transversity and fragmentation functions for up and down quarks, study transverse momentum distributions for valence and C quarks, study quark orbital angular momentum. That statement I put in there because the slide I took it from had it, but I think there's a challenge in general in my thinking of how actually one goes about getting at the quark orbital angular momentum, and at least I'm unaware so far of how you do that theoretically or experimentally, but I think many people are thinking about it. And combining with the world data from high energy facilities, they can study Q-squared evolution, much better understanding of the three-dimensional nucleon structure in QCD. So this is another thought that people have for the future. And this shows you, for one example of what these kinds of experiments would accomplish. You see the running of sine squared theta W, the electroweak mixing angle, as a function of the Q of the reaction. You see sort of existing results from LEP, from neutrino deep inelastic scattering, from an ongoing experiment at Jefferson Lab called Q-weak, and another point. And then you see what Mahler a new analysis of Q-week data that incorporates greater statistics would yield and a deep and elastic electron scattering. So you could see they could improve on the current statistics quite a bit and look for physics that goes beyond what we presently know about this standard model. The other thing that's sort of an outlook at Jefferson Lab is searching for a new boson conjectured, if it exists, to be very weakly interacting. That's why we haven't observed it yet. And you see the exclusion space for some values of the coupling, alpha prime over alpha, versus the mass. And so presently there's been a test called APEX that's just sort of mapped out this tiny blue slice right here and said, well, it's not in that place. But if they do the full APEX experiment they would like to do, they would map out this larger blue space. They also have notions of doing what's called a heavy photon experiment or heavy photon search, would be these brown areas, and also another experiment called dark light here. And so this is the kind of boson, if it existed, which could help explain, for example, the G-2 result. You see that this is the area that would be favored by G-2. So this would be a search for a new GeV scale force carrier. You can make your own judgment on whether you think this is a realistic possibility or not, but certainly nobody's looked. And it was a focus of the recent intensity workshop convened by Heinergy and Nuclear both. And so I think there's interest in taking a look at this. At the moment, the sort of outlook here is that this would have high energy funding, but we'll see where that goes. And they have some capability both with a free electron laser and CBAF that they could use to explore this. Okay. So these are the 21st century science questions that they're focused on: the role of gluonic excitations in the spectroscopy of light mesons, the missing spin in the nucleon, a novel landscape of nucleon substructure through measurements of new multidimensional distribution functions, something that's also of interest here, of course, as is the missing spin in the nucleon. What is the relation between short-range nucleon-nucleon correlations and the partonic structure of nuclei, and what evidence is there for physics beyond the standard model, and can we inform what that physics might be? And so these are questions they're focused on. So remarks by me. When I look at this, it seems to me, so there's an investment that's just been made in this facility of about $310 million to upgrade it to 12 GeV. It seems to me, looking at their physics menu, pretty clearly there's a decade plus of compelling science opportunities which could be addressed. Could, because there are things that can affect that. One could imagine that going forward, realizing the potential of that $310 million investment would be a reasonably high priority for the community. The more substantive experiments, and I'm going to say this in each subprogram, but I say it also here to begin with, the more substantive experiments like Mahler or SOLID are going to have to compete with other opportunities across the nuclear physics portfolio. And all such experiments, in my humble opinion, even more so in the past, are going to need to be in the rewrite textbooks category of impact. I think as we go forward, despite our efforts at outreach and perhaps some relief that we would get near term in the budget, in the longer term, I think just given the outlook for the country, budgets will be constrained. And so it will be even more important to select experiments of the highest impact, and it won't be perhaps good enough just to be a good experiment that's going to get a solid result. You may need to have a great experiment that's really going to rewrite the textbooks. And so that's a personal opinion. We try certainly to do that now, but I think we may even try harder because the resources will be so competitive. Okay. And one could imagine a program of detector upgrades and new detectors here similar to the evolution of RIC. For those of you who've been around for a while, you remember that RIC started with sort of a baseline configuration, and then there was additional experimental equipment, which was very important for the RIC capability. And since then, there's been, Ed's nodding because Ed knows it quite well because he's been in the firing line for a long time. There's been a series of upgrades that have each been very important to achieve certain physics reach. And one could imagine here that for that decade, I mean, you would have something similar to that because you would like to realize the potential of the investment that the nuclear physics community is putting into that facility. Okay. So moving on to heavy ions, of course, you get more red than the last one, at least in my opinion. And so, of course, the first bullet sort of belongs entirely here. QCD and its implications and predictions for the state of matter in the early universe, quark confinement, the role of gluons in the structure of the proton and the neutron. All of those are things that you intend to address either with the heavy ion program or the spin physics program. And there's a future beyond that we'll talk about in a little while. Developing a new standard model of nature's fundamental interactions. That's perhaps not quite as strong as the first bullet, but you do touch on that with some of the work that goes on here. And then, of course, all the things in red on the left-hand side, the phases of strongly interacting matter and the roles they play in the cosmos. What does QCD predict for the properties of strongly interacting matter? What governs the transition of quarks and gluons into pions and nucleons? What the role of gluons and gluon self-interactions is in nucleons and nuclei. I mean, that was a Jefferson Lab specialty, but you touch on it here as well, I think. And what determines the key features of QCD and their relation to the nature of gravity and space-time, which was sort of an unexpected intellectual connection that I think sort of came up in the course of the RIC research program, which was quite fascinating to watch. And then question marks in those other areas as well. Saying it very plainly as I can, the science productivity at RIC, and I can say this even though I was here, I think anybody would say the same thing. The science productivity at RIC over the last decade has just simply been stunning. It's just, if you were here in the first moments of RIC, I mean, the data just poured out of the accelerator, and the theorists who all were working extremely hard had a hard time keeping up. I think that's fair. Would you agree with that, Mike? Yep. So it's just been, and Mike agreed with it. That means it's true. All right. So, I think it's just been unbelievable. This is sort of an iconic plot that I think was sort of put together around the time of the last quark matter, and sort of shows that at RIC you may have a really unique capability because you're in a sweet spot which spans both the transition to deconfinement, but also you can go below that. And so you can actually, in principle, turn it off and see what happens as you go through the transition. And so on the left-hand side, you have the local parity violation result from STAR, which seems to do something quite different when you go below 39 GeV. I know there's still a lot of theory discussion about the exact interpretation of that, but certainly it looks like there's a transition when you go below 39 GeV. The constituent quark scaling, which perhaps may not be completely understood yet theoretically, but certainly looks like it changes its character when you go below 39 GeV. And the high PT hadron suppression, which changes dramatically when you go below 39 GeV. So it looks like, first off, you're in a sweet spot. That's very good. Second of all, RIC is probably the most versatile, capable machine ever built, as far as I can tell. You can accelerate unequal species and therefore try and disentangle geometric effects in the flow from fundamental effects and really get at, for example, the shear viscosity per unit entropy. You can, and one of the recent achievements, of course, which is very important, is the acceleration of uranium on uranium. You can accelerate polarized protons with their spin polarized in any direction you want. And it's just a tremendously versatile machine. So it's truly remarkable. Your research focus, you continue to elucidate the fundamental properties of the perfect liquid that was discovered here in 2005 to determine the contribution to the proton spin from gluons, C antiquarks, and C quarks to study transversity and advance our understanding of contributions from orbital motion within the proton. And also to address other scientific targets of opportunity. And so one of the ones, as you know, that came up last year that was very nice was the finding of the anti-helium-4, right? Which at some level everyone perhaps expected anti-helium-4 was there or should have been there. But the technical tour de force to actually make that measurement is really quite impressive. Okay. The other thing that's been really impressive at RIC is the unanticipated intellectual connections to hot QCD research. And so, as I hinted at a few moments ago, I mean, one thing that was really unanticipated is that RIC could become a laboratory to test string theory predictions. But in fact, string theory studies of black hole behavior led to the prediction of a conjectured quantum lower bound on 8/S, the perfect liquid. And in fact, there is this synergy between studies of string theory and the results at RIC. Ultra-cold atomic gases, like the one that's pictured on the left, at temperatures even 10 to the 19th orders of magnitude below the quark-gluon plasma, can also be nearly perfect liquids. And so what we discover as we look closer is that any strongly interacting system can have this perfect liquid type of behavior. And I think that's an enlightenment that also was not obvious when the RIC started its research program. Similar liquid behavior is seen and studied in a number of strongly correlated condensed matter systems. There are papers by Dima Karzaev et al., and perhaps some of you here that I'm not quoting, but certainly deserve recognition about how the degrees of freedom in the quark-gluon plasma shed light on how things work with graphene, for example, just as one example. Symmetry violating bubbles in the QGP, analogous to speculated cosmological, baryon-antibaryon imbalance in the universe, and the power spectrum of flow analogous to power spectrum of a cosmic microwave background. So there's a whole range, which is the way science is supposed to work, actually. You start out studying something that you really have just a pure scientific interest. You just want to know how that works, and you don't have any idea of how it's going to connect to something else or how it might be useful. And lo and behold, you shed light on something important in a whole new area of scientific endeavor. And so, I mean, that's the way, good science works. That's also the reason sometimes it's hard to defend, because sometimes the connections can be very circuitous, even though in the end they have huge impact, and they can take a very long time to develop. And so I think this is by no means the end of the story on the impacts of RIC in broader impacts. I think, at least the way I view it, I think it will be a long time before people fully understand the real importance of what's been done here. And you are doing more yet. So I think, it's all very positive. So it's all wonderful. But I would say, at least this is, again, my personal view, there's some very important homework still left on the table, despite a lot of experimental and theoretical work. So it was shown already in Budapest in Quark Matter 2005 that charm hadrons are as suppressed as light quark hadrons. And so I still remember Yasuyuki following me down the hallway, yelling at me that the star results were all wrong. And he was only partially correct. But the part he was correct on, we fixed later. Okay. It's 2012, and we still don't fully understand why that's the case. Now, there are some very good reasons why that's true. For one thing, you needed to build new microvertex detectors where you could really look at those particles that decay, the charm and to some extent bottom particles that decay. And the RIC energy is just on the border for some of the things you would like to study, like upsilon and those things. So, but I would say this is a really important thing that I think RIC has to resolve. I think it speaks to, the transport of these particles through the plasma, I think, is telling us we don't understand the degrees of freedom and why things interact so strongly. I think somehow at the end of the day, whenever that is, if we haven't answered this question, then we've really not achieved fully what we should have done. And so I think this is imperative that this gets resolved. New complementary capability at LHC may help. And we're, of course, trying to provide some new instrumentation and new ideas at RIC. Near term, those are in the form of those microvertex detectors I mentioned a moment ago. Longer term, there's some new ideas. But before I get to those, let me just say, you have now competition. It's collegial competition, but also competition in the beginning of the heavy ion research program at the LHC. The way I view that is what they've done, at least in the beginning, is confirm your discovery of 2005. And so this is a chart that addresses the jet quenching that's being observed in the collisions at the LHC. This is happens to be from CMS. On the left-hand side is a cartoon. I just took the bottom half and reflected it up as a sort of example of what you ought to see if, you know, two quarks have a hard scatter, or a quark and a gluon. You ought to see two jets coming out with more or less equal transverse momentum. In fact, what you see is on the right-hand side, and that's data. So you can see quite clearly how, you know, on one side where the parton came more or less straight out, you got the jet you expected, and on the other side, the energy of the initial parton got distributed among many softer modes. And so I think these results show that the new form of matter, believed to have influenced the early universe, has unique properties, interacts more strongly than any matter produced in the laboratory, and really says that you know, LHC is also a laboratory. It confirms what you did in 2005, what you discovered in 2005. Also said this laboratory is open for business as well, to also give complementary information on the matter at the LHC. And you see that. So that was you know, jet imbalance. This is the iconic nuclear modification factor RAA, and of course as a function of PT. And you see, you know, very nicely that the LHC data are mapping right on to, you know, where the RIC data leave off. So again, you know, a nice confirmation that everything that was done here so far is right on target. And one of the differences, however, at the LHC, of course, is the higher energy. And so they can really get to the bodymonium states, such as the upsilon. So, I mean, they will be providing data that you have a difficult time reaching here just because they have the higher energy. That said, they're also in a different regime. And so I think, you know, one of the most important things will be the comparison of the data in the two regimes, to the extent some of these Corconia states can also be measured here at RIC. Okay. New ideas I mentioned a moment ago. So this goes to one of the thoughts that people came and briefed us on at DOE. It's a real question of why there's such strong coupling in the plasma. A small shear viscosity per unit entropy density actually implies strong coupling in the plasma. The Q hat, which is the measure of sort of the transverse spreading of the energy, is proportional, I think, to the temperature to the third power divided by 8 over S. And so if you have a small 8 over S, you have a strong coupling. But how does the quark gluon plasma transition from strong to weak? And it looks to be a bit weaker at the LHC. And is this transition associated with changes in quasiparticles, excitations, and strong fields? So one of the ideas that people have to try and take a look at this is looking at dijets and the imbalance of the dijets. So this is this is work by Coleman Smith, pointing out that dijets at RIC scales are likely to be strongly modified by the presence of the deconfined QGP medium. Now basically, that you can see here how as the jet asymmetry increases, how that's correlated with the running of alpha S. So, you know, when you have a fairly weakly interacting system, which is in the blue, you don't have such a strong asymmetry, but by the time you get alpha of 6.6, you see you're getting a fairly sizable asymmetry. And so the idea is to use dijets to try and get at this question of the strong coupling and how it changes. And this is a Haijing simulation by these folks that shows, you see, for different centralities, how this asymmetry can change. So for 0 to 10% central gold-gold, you get the green curve showing you have a sizable asymmetry. For the more peripheral collision, you see in blue, you don't see that dramatic an effect. It seems to be pretty independent of what size jet radius you decide to use, whether you use an R of 0.2 or an R of 0.4. Although I think, as far as I understand, one of the tricks people plan to use to try and prevent the underlying debris from entering into the estimate of the jet energy is to use a fairly small jet radius of about 0.2. So I perhaps didn't get that quite all right in detail, but certainly there are people in your community who can fill you in on everything you want to know. But where this leads to is an idea for an upgrade of Phoenix called S-Phoenix in its first phase. And so they would really like to focus on jets for some of the reasons I've explained. And in this concept, there's a hadron calorimeter outside an electromagnetic calorimeter, and you see a solenoidal geometry which is pretty much hermetic within pseudorapidity of 1. So that's one idea. STAR also has a plan for evolutionary upgrades. So these are longer-term things for the future, which would lead to compelling heavy ion physics beyond what's already being attacked or addressed at the moment. And so I think these are ideas that are being fomented, and we look forward to hearing more about it. So on this, what my remarks would be is there appears to be a decade of compelling science opportunities which could be addressed in the RIC heavy ion portfolio. And so you see appears to be is different from the previous one when I said there's clearly, and one of the reasons for that is, as I said a moment ago, I think these ideas are still being fomented, and so we still need to hear what the case is and how compelling it is, and so that's work that's ongoing. I didn't mention it, but efforts in QCD thermodynamics, such as those led by Fritjof, and more generally in nuclear theory, are going to remain essential for the interpretation of the relativistic heavy ion collision. So nuclear theory remains very important in this outlook. And as I said for the last subprogram, the more substantive proposed experiments are going to have to compete across the program and are going to need to be in the rewrite the textbooks category. One thing so the next bullet I'm going to talk about, but I don't want anybody to go out of this room thinking that there's some crisis or something the associate director said that's a problem. But I wanted to just voice it because I think it's something I think about. In the logical extreme, so, and who knows how far that is out, right? I mean, that could be a decade, that could be 2 decades, who knows? The heavy ion campaign is going to complete its mission. And so, at least in my thinking, a higher energy nucleus-nucleus collider seems unlikely. And so at some point, to be determined in the future, the experimental opportunities in experimental relativistic heavy ion physics are going to become exhausted. So I'm not talking about the present, and I'm not talking even about the near future, but I'm just talking about when I think about way, way out, it seems to me that there's a heavy ion campaign that's been going on, and eventually you will mine all the opportunities. And then what comes up in my thinking, and I may be long gone by then, so it may not be my problem, is what will this community want to what will they think of doing next, right? What will they pursue after that in the relativistic nuclear physics community? And so it seems to me, when I think about it, and I don't have an answer to this, it's sort of, as I said, meant to be a bit provocative. I would guess that something that would be attractive is the area of fundamental symmetries, because in essence, the focus here is on the early universe, and so the fundamental symmetries program is focused on the early universe. So I can imagine that would be more attractive than other things that one could imagine in the rest of the nuclear physics portfolio. So I don't want to make a big point on this, but I just point it out as something that I think about from time to time over my glass of wine and sort of where this will ultimately wind up. Okay. So one possibility, of course, where things could wind up is an electron-ion collider, and you're working hard to document that science case and demonstrate feasibility. As you know very well, there are 2 concepts for what the machine might look like. This would, in both concepts, have to be a high-energy, high-luminosity polarized EP and EA collider with suitably designed detectors. And so this, of course, is one possible area of future interest for relativistic nuclear physicists. The fundamental questions that would be addressed: how do the gluons contribute to the structure of the nucleon? What role do the gluons play in determining the spin structure of the nucleon? And what the spatial distribution of quarks, gluons and C-quarks are in the nucleon? How do gluons contribute to the structure of nuclei? What are the properties of high-density gluon matter? How do fast quarks and gluons interact when they traverse through nuclear matter? And so to address those things, the kind of research you want to do is precise imaging of the C-quarks and gluons in the nucleon, and exploring the new QCD frontier of strong color fields in nuclei. So those would be some of the scientific interest in going to a future electron-ion collider. The science, I think this might be a bit redundant, precision measurements of delta Q and delta G by inclusive and semi-inclusive deep inelastic scattering, the spin puzzle, measurement of gluon general parton distributions and transverse momentum distributions. So I think there's an opportunity here to sort of do tomography in 3 dimensions, longitudinally and transverse, that hasn't existed before, which is very exciting. I mean, one could find that one flavor of quark prefers to be in the center of a nucleon, and the other flavor of quark prefers to be more on the periphery. You're sort of, I think, at a juncture similar to the early 1900s when people really didn't understand the atomic nucleus or what was in the core of a nucleus, and were postulating plum pudding models and other things until Rutherford did his scattering experiment. So I think it's actually a very exciting prospect to be able to make these kind of tomographic research studies. Study of extreme high gluon densities. I mean, do the color fields get so strong that basically you're back to classical physics? High energy beam polarization and full acceptance detector. With all that, you have also capability to explore precision electroweak physics and electroweak's spin structure functions. So there's a lot of interesting things one could imagine. This is a bit what I was talking about a moment ago. At the moment, we sort of deal with information where a lot is integrated out in terms of what we might know from, for example, the Wigner distribution. We deal with parton distribution functions, which integrate out a number of the important variables, or form factors, which also integrate out a number of the important variables. But if we can actually measure generalized parton distributions and transverse momentum distribution PDFs, then we can really get to this kind of 3-dimensional imaging, which I think will give us for the first time a real understanding of what the quarks are actually doing inside of protons and neutrons. Okay. So speaker's remarks here about the electron-ion collider. And so one question that I have is, if you build it, will they in fact come? Right? And that's directed primarily at the heavy ion community. It's not a priori obvious to me that people who are very interested in heavy ion, relativistic heavy ion physics, are as interested in the science of an electron-ion collider. I think they probably are interested, but I don't know that that's completely sort of, that community's completely warmed up to that physics yet. It seems pretty clear, and I don't think I'm telling anyone here anything they don't know, that strong investment by both the present RIC and JLab communities is going to be essential wherever this facility gets built, presuming that it gets built. Of course, that's a big question too. It seems to me that both communities and both labs have to have a viable future path in order to have the sort of robust participation within the broader nuclear science community that's really going to support putting that kind of investment into this kind of facility. And I think that's something that really needs to be worked on, because the science case really hasn't been, a lot of work has been done. I don't mean to be negative at all. But I think the case still has not been presented to or embraced by the wider nuclear science community or the funding agencies. At some level, that's natural because there's a progression, and I think this will happen naturally as we get to a real long-range plan exercise. But it hasn't happened yet. I think spin physics will be an essential component of the physics case, but I think it would be challenging to propose spin physics as the primary science motivation. So I think it's a very important thing, but it can't be the main thing. That's a personal opinion. And in discussing the spin physics case, I think it's going to be essential to articulate what is really new and could fundamentally advance our understanding. Sometimes when I hear talks about the spin physics related to this concept, it sounds an awfully lot like the arguments that I used to make for STAR when I was defending spin physics a while ago. And so people talk about measuring delta G. I'm sure it's more sophisticated than that. But I think there's some work to do to really articulate what's fundamentally new about the spin physics that could be done at this facility, and why is it not just what's been done before, but something that's really going to advance our understanding. And the other thing is, I don't This is just a conjecture, but in the era of constrained resources, it's possible that in the future there could be one QCD user facility. That doesn't mean there could not be more than one lab with a very robust program of QCD research. But there may not be enough resources to have two QCD user facilities, major user facilities, like an electron-ion collider. It's fairly obvious, I guess you wouldn't build two of them, but I think maybe you would if you could. So I think this is something, even though people somehow understand it, don't necessarily think about. Let me move on to low-energy nuclear physics program, and I'll try and speed up a little bit here. Again, you see in the red what I think this program is supposed to deliver. In this case, I've swapped out QCD and put in nuclear and nuclear astrophysics, and you see they're on the hook to provide all those things. And fundamental symmetries and neutrons, all those things as well. So one thing that's operating at the moment is the Argon Tandem LINAC accelerator system. And our new investment there is something called the Caribou upgrade, which stands for Californium Rare Isotope Breeder upgrade. It's a pretty simple idea. You take the fission fragments from californium, you use a gas catcher to catch them, and you accelerate them down the beamline so that scientists can do research with radioactive beams. So it's a poor man's way, if you will, of creating a radioactive beam facility, but provides some very important capability. So that's sort of near term what our new investment is, and we expect the research program on Caribou to begin this year. It's actually, in DOE parlance, a notable outcome for Argonne National Laboratory. But if you talk about the further future, where we see the niche for this facility, which we do imagine to continue to run, is as a unique premier stable beam facility for research on nuclear structure and nuclear astrophysics, complementary to the facility for rare isotope beams. Of course, that's the concept we have for providing, world-leading capability in nuclear structure and nuclear astrophysics well into the future, decades into the future. This is sort of the public relations plot. It will increase, in short measure, the number of isotopes with known properties from 2,000 to 5,000, but that's not really the news. The real news is that from looking at the properties of those kinds of measurements, we will be able to do important research on nuclear structure, finding out where the ultimate limits of existence are for nuclei. Where is it no longer possible to construct a nucleus, for example? We don't know that at the moment. Nuclei that have neutron skins, synthesis of super heavy elements, and there's that campaign is actually heated up a bit, and there's ongoing research at GSI and also Dubna, and the Americans are collaborating on that. Nuclear astrophysics, the origin of the heavy elements and explosive nucleosynthesis, composition of neutron star crust, fundamental symmetries, atomic EDMs, and weak charge. So those are a few of the topics. But I think what's really, let's see, I don't get there quite yet. So these are examples, and there's much more going on, but examples of the kinds of research going on in the area of nuclear structure and nuclear astrophysics. And the particular thrust is understanding what happens as you add more neutrons near the neutron drip line. So that's the line where if you add one more neutron, it immediately decays to a state with one less neutron. So, but understanding that part of the isotope table, which so far has been inaccessible, just technically we can't get there, is going to be one of the main foci of this kind of research. This is an example actually from the Hollofield radioactive ion beam facility, which was shut down this April in favor of a future with a better capability of finding a new doubly magic nucleus, tin-132. That's particularly interesting because if you transfer one nucleon now onto that doubly magic nucleus, you have a sort of a core with one nucleon orbiting around, which becomes a laboratory for nuclear theory to sort of test what you would expect for the behavior of that one nucleon circling around a closed shell. So speaker's remarks here. What I think is particularly powerful is not sort of a stamp collecting and measuring thousands of individual reactions. That's a tour de force that needs to be done, but that's not what's most important. What's most powerful is again the promise of significant theory advances in lattice and also computationally intensive density functional theory, which will really allow us to come to a more solid predictive basis for nuclear structure and right. So one example, for example, in low energy nuclear physics, lattice QCD folks, and so one of those folks, which some people here may know, is named Wick-Haxton, planning to extract nuclear forces from LQCD, which could be used as input to their shell model and related codes. And that would be something of a breakthrough, since currently people get their nucleon and 3-nucleon forces from experiment rather than from QCD. So here again, I think the real power comes in from the comparison of nuclear theory with an extensive experimental data set. As I've said, for all the subprograms, the more substantive experiments are going to have to compete across the program. And for FRIB, as for JLab, as for RIC, one could imagine sort of a series of upgrades similar in nature to the evolution that happened at RIC in order to realize the real potential of this facility, presuming it gets built. Okay. Other comment? Oh. So we have other, actually, investments in fundamental symmetries. I'll try to go really quickly. One is trying to measure a neutron electric dipole moment and set a limit at the level of 10 to the minus 28. If we could do that, we would begin to challenge whether baryogenesis could be the origin of the matter-antimatter asymmetry in the universe, which would be a very important thing. There's some very important R&D ongoing, and it's not clear we can do that yet. But those people are working hard to demonstrate that we could. If we could, then we'd try to start up an MIE. This experiment would be, I believe, in the sort of $40 to $50 million class between DOE and NSF. It's a fairly large collaboration, so that's something that's sort of ongoing. In the area of neutrinos, we have investments in two places. One I'll speak about in a moment, but we also have concerning the neutrino mass, one endpoint experiment that we support in Katrine. This looks very much like a scene from the War of the Worlds, but in fact that's the vessel here going through the streets of some small German town where everybody came out to see what happened. And so, I mean, this is now in place. It's gone a bit more slowly. I expect that this will yield a result on the time scale of 5 to 10 years still. It's going to be a while. And the limit it will put is something of order 200 millieV, which by itself is not exceptional. I mean, even from astrophysical processes, we already know that that's something of a limit. What would be important about this is it's the first terrestrial direct measurement that's model independent. And so that would be an important confirmation that, in fact, that limit is a good one. So this work is ongoing. We don't have a huge investment, but the result could have some importance when it really comes out. Our more sizable investment in neutrino physics is in neutrinoless double beta decay. And we have a demonstration project which is about to go underground at the Sanford Underground Research Facility at the Homestake Mine in South Dakota. And so they will be trying to reach a certain limit to demonstrate that they have the sensitivity to go to a ton scale experiment. That experiment's going to take a bit of thinking, at least in my estimation, because it's a very challenging business. So the ton scale experiment in principle imagines that it can reach a sensitivity in so-called M beta beta, the effective neutrino mass of 50 millieV. So oftentimes when people talk about these kinds of experiments, they talk about the neutrino mass when they're actually talking about this M beta beta. And M beta beta is not actually the neutrino mass. It's a combination of eigenmasses of neutrinos multiplied by some phases that we actually don't know yet. So you have to be a little bit careful. The ton scale experiment would put a sensitivity on of 50 millieV. And so this is showing you where you would be in this plot of M beta beta versus the lightest neutrino mass if you had an inverted hierarchy or if you had a normal hierarchy. And as I said, this is a challenging business. If M beta beta is greater than 50 millieV, then if the neutrino is Majorana, then the Majorana experiment should detect it. If the Majorana experiment doesn't detect it at a level of 50 millieV, it won't be immediately obvious whether that's because the neutrino is Dirac. We won't be able to tell that. Or whether because perhaps it's a normal hierarchy and not inverted hierarchy. If somebody happens to tell you which hierarchy you have, if, for example, the NOVA experiment in high energy physics determines what the hierarchy is, whether it's normal inverted, and you could reach a sensitivity of, say, 10 millieV, which is below what Majorana currently says they can reach, and you didn't see anything, then you could say that the neutrino is a Dirac neutrino. So, I think before we launch into this ton-scale experiment, there's going to have to be a very considerable look at, what we think we will really get out of it. We're not averse to taking some risk. That's what science is about at some level, is taking risk. But we want to make sure that for the level of investment this would take, that we really would be guaranteed at least some very important payoff. And so I think that's something we'll have to take a look at. There are a number of horses in the zero neutrinoless double beta decay race. One that you may have heard about or will hear about if you didn't is called EXO. That's an experiment that's being done at the waste isolation pilot plant. The spokesperson is at SLAC, and the R&D for that, through the R&D phase, it's being supported by high energy physics. Within the DOE, the Office of Nuclear Physics and the Office of High Energy Physics have agreed that nuclear physics, the nuclear physics program, is the steward for neutrinoless double beta decay. So in the future, whatever technology, whatever experiment gets selected for the really second or third generation experiment, that stewardship will be in the Office of Nuclear Physics, even though at the moment the R&D for EXO is coming from high energy physics, and for Quarry and Majorana demonstrator, that's nuclear physics. So you see the projected sensitivities these experiments are going to get to as a function of year. In fact, EXO is about, if they haven't already, to put out a paper that shows that they're right on track for what's expected in 2012. They're right around here in the sensitivity that they've already shown. And so they're in some ways challenging the rest of the competitors to really do as well as they can. And so I think we'll see how things turn out. Not too much more. I'll just mention that one thing we try to highlight when we talk with the higher-ups is that in the process of doing this discovery science and sort of standing on our toes to stretch with new technical capability to try and reach new science opportunities, innovation comes out and new technologies come out. And this is an example. Atom trap trace analysis, the reason this was pursued in nuclear physics was not krypton dating of water aquifers. It was because people really want to look at atomic EDMs, for example, of radium. But in the process, they developed this capability for isolating even a single krypton atom in a magneto-optical trap. And so now they can use a certain isotope of krypton to date the water in ancient aquifers. And they've done this for the Nubian aquifer in Egypt and a number of aquifers around the world. And so if you pay any attention, if you listen to NPR, let's say, a few weeks ago, maybe a month ago, there was a story about, in Washington, there's an awful lot of intelligence agencies, quote unquote, right? I hope I still have a job. Now I've confused myself. Oh, the point is they wrote a report recently that they submitted. It was sort of a collective report from all the agencies, which said that in the future, the real contested resource in the world will not be oil, it will not be fuel, right? It will be water, right? And so it's very important to understand the dynamics of how aquifers evolve, how they're refreshed. If you take enough water out of them, will you ruin them forever, or can they be replenished? And so this kind of thing is very important. It's actually been picked up by the IAEA as an important program that they're pursuing. And it came from this capability from nuclear physics because someone wanted to measure atomic EDMs and develop this capability. So it's that kind of story that we try to pass along. Okay. So speaker's remarks here. So for neutron EDM, the science goal continues to be strongly motivated. The R&D continues. We expect a decision point, sort of a go, no-go decision point on that experiment within about 2 years. There was an NSAC committee, sub-panel that looked at this, and they said that, if 2 years goes on and we really haven't gotten much closer to resolving these R&D issues, then essentially the experiment's going to lose its competitiveness in a worldview because there are other experiments that will also be done that will be able to reach those limits. And so on that time scale, and that was 6 months ago when that finding came out, I mean, we will be making a decision on whether we go forward with that. On Majorana, I think a necessary condition to proceed will be whether the Majorana demonstrator in fact reaches a sensitivity level required in the Sanford underground research facility. If it doesn't reach that sensitivity level, I think it would be very doubtful in my mind that investing in a ton-scale experiment would really be a way to go for nuclear physics. And of course, we'll have to also look at the status of neutrino science when we get to that decision point. Do we know what the hierarchy is? I mean, has NOVA already told us that so that we're on some firmer ground in terms of the potential payout of the experiment? And I haven't sort of talked a lot about it here, but since this is Brookhaven, I want to make sure you understand we noticed that there's an idea percolating for proton EDM. And the same statement, of course, about how important it will be for the experiments to be of the highest impact and caliber. Okay. Nuclear theory, I won't say much. I've said all the way through that it's just absolutely essential that nuclear theory is what ties it all together and really allows the experimentalists to deliver important results. And so it goes without saying that there's an essential role for nuclear theory. I don't know that that needs to be mentioned. I will point out that one thing we tried, which I think is very popular and we will continue to try if resources permit, is topical theory collaborations. So this is getting together a number of theorists from different institutions focused on a single important problem in nuclear physics that needs to be resolved for a particular community. And so we have 3 of them now. They're about coming up for their midterm review. In the future, if we can, we will do this again. Isotopes, these are the isotopes we produce and the logos of the companies that use them. This is actually a very important little program for nuclear physics. The appropriation is rather modest. It's about $20 million out of the $540 million or so that we have in 2012. But the impact of that $20 million appropriation is probably over $1 billion. So it's a very important program, and it helps demonstrate relevance of nuclear physics to stakeholders in the Congress and others. So it's very important. We have an early career research award program to promote and mentor or promote mentorship of young scientists. I think you're probably all aware of that program. The only point I want to make, it's a commitment in asymptopia to continue this program. So by 2014, we'll have reached asymptopia, and that's a commitment on the part of our program of about $10 million in sort of awards that have been made, and then a new solicitation each year. So it's a source term for refreshing the scientific talent in the field and helping young scientists get a start and to further their careers. And so that will continue. So that's the second bullet here. But the first bullet, I'll just say in passing that nuclear physics continues to seek an opportunity to address the NSAC isotope recommendation for a dedicated isotope research facility. So we haven't figured out how to do that yet. That idea is getting very long in the tooth. We have some notions. We haven't figured it out yet, but we also haven't given up on it or lost sight of it. Okay. Nuclear physics funding. The short story is the black curve is the resources that would be needed if you did most of the things that were identified in the 2007 long-range plan. The bars are appropriated dollars sort of as we've gotten them through fiscal 12 and as requested by the president in fiscal 13. And so, I mean, you could see at a glance that we have a challenge because the black curve's going up and the appropriated dollars are rolling over. And so we have to figure out how to deal with that gap and the eventuality, whether the gap gets smaller, gets bigger, or stays the same, we have a challenge to figure out. Okay, that's the grist of the NSAC subcommittee that's been put together. This is the charge to them. I don't want to dwell on it. I'll just want to point out that this charge has been made in the context of the 2007 long-range plan. Right? And so this is not a full-out long-range plan exercise where we're going to try and identify every possible avenue of research opportunity going forward. This is really taking a look at what was identified as priorities in the 2007 long-range plan and figuring out how we would implement that plan if we have less resources than were assumed in reaching that plan. Okay. Those are the people who are on it. We try very hard to make a balance across nuclear physics and to make it very fair across the different sub-programs. I'll leave, that'll be in the file so you can see who it is, but you can also go to our website and find out who it is. And the other point I wanted to make quickly is that the chair of that subcommittee, who's Bob Tribble from Texas A&M, who we are all in his debt because he did this once before, as some of you know, in 2006. It was a very, very difficult exercise, and he did just a superb job. He said no at least 3 times to being the subcommittee chair here, and we finally convinced him that it was important enough he really needed to reconsider. So we are in his debt for doing that, but one of the things he said is important is that it be a very open and fair exercise, and so you're invited, if you wish, to have input to that, and so he's put a website up where you can have input. He suggested that you might want to do that through your user organization rather than having a lot of little different things. You might want to caucus and decide what to do as a user group, but there's no prescription here. You can do whatever you want. You could go to it yourself and say what you think. You could work with your user group and do it that way. So the outlook. All said, I think the future of nuclear science in the United States may not go exactly as we had envisioned it, but certainly I'm convinced, hopefully I've convinced you a little bit, I certainly haven't touched on everything, that the future remains rich with science opportunities. And so, I think, as I said, we may not have quite the resources that were imagined in the long-range plan, but there's still significantly more than $500 million invested by the United States of America in world leadership in discovery science and nuclear physics, illuminating the property of nuclear matter, creating new tools for science knowledge and technical advances, and making strategic investments in tools and research so the U.S. will have premier research capabilities in the future. So I believe nuclear science will continue to be an important part of the U.S. science investment strategy to create new knowledge and technology innovation, which supports in a very fundamental way, and you're invited to help us sort of carry this message wherever you go, supports U.S. security, economic security, national security, and very importantly, competitiveness. Nuclear physics program really contributes in many ways to the competitiveness of our industries, and I think that message really hasn't gotten out nearly as far as we could take it. So I'm optimistic about the future. I think we're going to have to work together, and we have a challenge to get through. I think the NSAC subcommittee exercise is in fact an opportunity for all of us to articulate the importance of what we do and what could potentially be lost if we don't have the resources that we imagine. And so we'll see how it comes out, but I think in general about the future I'm optimistic. Thank you. And yeah, sorry for running over.
I have a question in the statement. When we meet at the end, when do you expect to have a decision?
So I would think that would come on a time scale of about sort of a year and a half from now, something like that, Giannis. It's not that we fixed, a firm date and say on this date we'll make a decision. If they seem like they're really making, the kind of progress they should be making, of course we'll take that into consideration. But if we get sort of a year and a half, 2 years down the road, and it looks like, there's still very important questions and we're not that much closer to answering them, I think then the decision would be taken to sort of regroup.
The statement I want to make is on the proton EPM, the collaboration with welcomes a review on the proposal.
I'm sure you do. So let me make a comment to that because it also applies to proposals that we have from JLab. We try to be very careful about managing expectations, and before we really get serious about reviewing something, we want to understand how we would fund it if it came to us from the peer review that's really something we should fund. So from your view, that may seem like we're just sitting on our hands. We don't want to be viewed that way, but and that's not our intent. But we really do want to sort of not get the whole train moving and then find out there's no there, right? So, just a comment.